Today, we're diving into something called StackWarp. It's a brand new vulnerability, but it's not in your apps or your operating system. Nope, this one is hiding deep, deep inside the chip itself, targeting the very hardware that's supposed to be protecting our data.
You know, we all put so much trust in the cloud, right? We just assume the hardware is this impenetrable fortress. But what if that fortress has a secret back door, a hidden switch, completely off the books, that a clever attacker could just flip?
Okay, so how in the world does something like StackWarp even work? Well, before we get to the attack, we got to understand the defense. Let's talk about the tech that's supposed to be our digital vault in the cloud.
All right, here's the hero of our story, or so we thought. Confidential virtual machines, or CVMs for short. Think of it this way. Companies like AMD have this tech that basically wraps your entire virtual computer in this super strong encrypted bubble. The whole point is that nobody, not even the cloud provider, the people who own the actual physical servers, can peek inside. And that promise? It's a huge deal. The analogy they use is a digital safe deposit box. The bank, that's your cloud provider, gives you the box, but they literally don't have a key. It's supposed to be the ultimate form of privacy, right? Your stuff is safe, period.
But here's the thing. These CVMs, these secure bubbles, they don't exist in some magical void. They're running on real-world processors. And those processors are designed for one thing above all else, speed. And speed often means sharing. And that's where our problem begins. Okay, so let's talk about a feature you've probably heard of, simultaneous multithreading, or SMT. Intel calls it hyperthreading. It's this really clever trick where a single physical CPU core can pretend it's actually two separate cores. It's all about boosting performance, letting these two logical cores share the work and the internal machinery of that one physical core.
And this is the classic trade-off, isn't it? It's great for efficiency, it makes everything faster, but it's exactly like having two chefs sharing the same kitchen. When they're working shoulder to shoulder, using the same countertops and tools, what if one chef can mess with the other's ingredients without them even knowing? Suddenly, that perfect isolation we were counting on, it starts to look a little shaky. So where's the weak spot? Where's the crack in the foundation? Well, the researchers dug deep and found it in a very specific, kind of obscure part of the CPU.
It's a component called the stack engine. Now, real quick, the stack is just like the CPU's scratchpad. It's short-term memory for whatever program is running. A stack pointer is the little bookmark that tells the CPU where it left off on that scratchpad. So the stack engine, it's a piece of dedicated hardware designed to make managing that bookmark super, super fast. It's one of those little performance boosters that just hums along in the background, totally invisible.
And this is the bombshell. After tons of reverse engineering and poking around, the researchers found it. A single, hidden, completely undocumented bit buried in a special register. A secret switch. And all this switch does is turn that stack engine on and off. But here's the critical, fatal flaw. When one of those chefs in the kitchen flips the switch, the other one doesn't know. The state isn't shared properly between the two logical cores.
Okay, so how do you turn this into an attack? It's this brilliant two-step move they call freeze-release. Here's the plan. Step 1, freeze. The attacker, running on the other half of the core, flips that secret switch to off. This basically tells the stack engine, hey, pause everything. It freezes any pending stack changes. Step 2, release. Just as the victim's secure VM starts running again, the attacker flips the switch back on. Wham! That frozen change gets released all at once and injected directly into the victim's program, completely messing up its bookmark, its stack pointer.
And get this isn't some random error. It's deterministic. The attacker has total control. They can choose the exact amount to warp the victim's stack. It's not a sledgehammer, it's a scalpel. They have a surgical tool to remotely mess with a program running right beside them on the very same piece of silicon. It's wild.
Okay, so a hardware flaw is cool for us nerds, but what's the real-world damage? What can you actually do with this? Well, the researchers didn't just stop at the theory. They pulled off some absolutely devastating digital heists. They showed 4 full attacks. We're talking stealing secret encryption keys, bypassing logins to secure servers, becoming the all-powerful root user on a Linux box, and even a complete takeover of the operating system's core. The whole shebang.
So heist number 1, stealing an RSA private key. Using StackWarp, they injected just one tiny, precisely timed error while the computer was creating a cryptographic signature. That one little fault was enough to break the math, letting them work backwards and pull out the entire secret key. Wow.
Heist number 2, breaking into a secure server. They went after OpenSSH, which is pretty much the gold standard.
With that surgical stack shift, they basically made the program jump right over the code that checks your password. It's like the bouncer asks for your ID and you just make him forget he ever asked. The result? They're in. No password needed. All right, heist number 3 might be the scariest for anyone who runs a server. They went after the sudo command. You know, the magic word in Linux that gives you God mode or root powers.
So here's how they did it. When you type sudo, the first thing it does is ask the operating system, hey, who is this user? The OS is supposed to reply with your user ID. But the attack hijacks the reply. Before the answer gets back to sudo, StackWarp changes it. It swaps out your normal ID and writes in the number 0, which is the special ID for the root user.
So, sudo gets the reply and thinks, oh, this user is already root. No need to ask for a password. And just like that, it hands over full administrative control. Game over. Complete system takeover.
Okay, so this is obviously a huge deal. The big question is, how do we fix this? What's being done to make sure our digital safe deposit boxes are actually safe? Well, there's a short-term fix and a long-term fix. The quick and dirty solution? Just turn off SMT for these secure VMs. Go back to one chef, one kitchen. No sharing, no problem. But the real permanent fix has to come from the chipmaker. It requires a special update called microcode. Think of it like a firmware patch for your CPU that teaches the stack engine how to behave and stay properly isolated. And here's the good news. The folks who found this didn't just drop a bomb on the internet. They followed a process called responsible disclosure. They went straight to AMD way back in March 2025, long before you and I ever heard about it. That gave AMD almost a year to work on a fix and get patches out to cloud providers and customers before the research went public.
StackWarp is just a wild reminder of how unbelievably complex the hardware we rely on every single day really is. And it leaves you with this one kind of spooky question, right? As we keep building more and more layers of software security on top, what other secret switches and forgotten backdoors are just waiting to be discovered, hiding in the silicon right under our feet?